talking about rates for different Diels Alder reaction. This one can't get in the right position. This one's stereochemically hindered. This one is similar to butadiene. And this is real fast because it's locked in position. And you can see these are diastereomers where this is stereochemically hindered. So here is a cis dienophile. And this comes up and I'm going to imagine it being underneath. A new bond forms and these hydrogens here get pushed up. These bonds here get pushed down when you form this ring. Now I'm going to get the same thing here, but only the trans diastereomer. And so we form a bond there and a bond there. And so notice here I have an ester group that's going away from me and an ester group that's coming at me. And here an alkyne. Fix that up so we wouldn't have any thing to look at there, but look at this thing here. You know, we form this new bond there and there. Where do these things go? But if you think of it being a syn addition event, where it either comes from the top or the bottom, things get pushed away. So both these get maybe pushed down and the hydrogen gets pushed up. Now notice here we have this part is the same, but the methyl group and the hydrogen have swapped positions. And so now we have one methyl group up and the other methyl group going away from. So here's a cyclopentadiene. This thing's gonna get pushed up. And then here's our 6-membered ring. But if we think about this, we could flip this over and have this aldehyde group coming out here. But nature likes it if this aldehyde, notice it has a p orbital here and a p orbital here. Here it's shown. Those can kind of overlap with the p orbital there in the transition state. And they call this secondary overlap. So the p orbitals of the electron withdrawing group on the dienophile have a secondary overlap with the p orbitals of the C2 and C3 in the diene. And so the exo and endo positions are labeled here. So here they're labeled. So that means we want to put this thing down in the endo position. There it is. So this thing here, we want to put those in the endo position. That one's pretty hard to see. So here's our diene. Here's our dienophile. And we have some group here. Of course, this is our electron withdrawing group. Now, fortunately or unfortunately, if I just say, all right, those electrons jump there, I'm going to form a bond. These are going to jump there, and you just write that on your paper, you would be correct. However, if you just willy-nilly see something like this and do the same thing, you say, oh, that's going to jump like that. Da-da, da-da. There's my ring. I can visualize it. And you draw something that looks like this. There's that group. Nature doesn't like that. That doesn't occur. That is called the 1,3 product. Where do they get the 1,3? Unfortunately, it comes in the same chapter where we talk about the 1,2 addition and the 1,4 addition. You don't want to try and find that on here and label this 1, 2, 3, 4. Here's all you have to do. It's this simple. This is the 1,4 product, and it's allowed. The 1,3 product isn't allowed. And why is that? So here's a picture of the product, and we say these electrons can jump down here and give us this thing here, and oxygen. We can draw these 2 resonance structure. You know, if I just said draw a resonance structure for this, hopefully you'd say, well, man, the only thing I can start moving is this unshared pair of electrons. Hopefully you could get to this. Then over here you might say, well, what am I going to do? I can't move those back. You can make these jump up. Probably put a carbocation there. Then you can probably move that over there. See, that puts the carbocation up there. So like charges repel each other, but opposites attract. So the minus reacts with the plus, and we get the 1,4 product. So the dienophile always looks like this, and this stands for electron donating. That's why they use D, donates a pair of electrons here. What if we have the electron donating group up here or down here? So 2 ways to look at it. If this is the quiz question and you just hook that up and put the double bond there, you lucked out. like I said before, you know, what if this thing is flipped? Or let me work with this thing here. If it's given this way on the exam and you say, oh, I'm an expert at Diels Alder, 6-membered ring, that bond moves there. All right, I have a D here, and I have my W there. What product is this? We'll just number these. This is a 1,3. And we might have learned from this one here, we don't like the 1,3 product. But nature likes the 1,2 and the 1,4. So you want to check this out before you go and before you go and do this, write this ring. Probably the best thing to do is put it together and see that it's the 1,2 product. Or if it's this way and you put it together and you get the 1,3, you're gonna say, well, something different needs to happen. And you say it should really be like that. It's gonna put W here. All right, D for dying or electron donating. That's gonna give you this charge separated resonance thing. And you can do the same thing with the dienophile. And they want to go together so that the opposites attract each other, giving you the 1,2 product. The Diels Alder reaction is an example of a Curie-cyclic reaction. Woodward and Hoffman predicted reaction products using their theory of conservation of orbital symmetry. Molecular orbitals must overlap constructively to stabilize the transition state. And dying contributes to the electrons from its highest energy occupied orbital. That stands for, we abbreviate that HOMO. Dienophile receives electron in its lowest energy unoccupied orbital called the luminal. 2,2 cycle addition of 2 ethylenes to form cyclobutene has antibonding overlap of HOMO and LUMO. Here's the antibonding interaction. Absorption of a correct energy photon will promote an electron to an energy level that was previously unoccupied. And so this is an electronic transition. And if we look at this, we see this is in the UV. So we say this thing is photochemically allowed but thermally forbidden. So now everything's set up with the correct molecular orbital symmetry. We won't focus much on that. But let's talk about ultraviolet spectroscopy. So this is common for analytical chemistry work. That means quantizing how much of something is in a sample. And it uses electromagnetic radiation in the UV and visible range. And it says here, conjugated dienes have molecular orbitals that are closer in energy. A compound that has a longer chain of conjugated double bonds absorbs light at a longer wavelength. So just to review, electromagnetic radiation, ultraviolet 200 up to 400, the visible 400 to 800. That's kind of stretching it on both ends. I think 700 to 420 is about what I can see. And then radio, you can see the energy falling way off at the radio. It's about all you want to take from this. So we're going from a pi bonding orbital to an anti-bonding orbital, promoting an electron. And here, it's this much energy corresponding to that wavelength, 686 kilojoules. And so this is ethylene. We just have one double bond. You can think of there's the electron, one gets promoted. Now over here we have a conjugated system, and we see that the energy has gone way down. So here's how a UV spectrometer works. And you measure the reference beam, helps for variations in the source. It'll take a difference, so it doesn't matter if your power is drifting a little bit with the light that's coming in. And you get a typical spectrum of absorption versus wavelength. And absorption is a unitless measurement because it's a ratio of the intensity coming in and intensity coming out. And we usually use this with Beer's law to measure concentration. We know what's in there, we just want to know at what concentration. So absorbance equals molar adsorptivity, the concentration times the path length. So if we want to measure this in some sample, say cyclohexene, something that doesn't have any double bonds, we measure the absorption here. and we can quantize how much of that is there. So here, a short wavelength, we just saw that this takes a lot of energy. This takes a little less. This isn't conjugated. So notice the big change here, that we're getting more and more conjugated. And now that we have all this conjugation, we're almost getting up into the visible range. So this is beta carotene, and look, 11 conjugated bonds. So this absorbs at 450. So if I absorb all of this, what color do you think beta carotene looks like? How many of you are into nutrition? You like to eat your vegetables? Well, maybe I'll ask a zoologist. What is orange and sounds like a parrot? Any guesses? What is orange and sounds like a parrot? A carrot, absolutely. And a carrot is a good source of beta carotene. What color is a carrot? Orange. All right, why is a carrot orange? Because it has a lot of beta carotene in it. So it absorbs all this blue-green, and what gets passed or reflected or not absorbed is that color, and that's why a carrot appears orange. So a lot of natural dyes and synthetic dyes, what do they have in common? They have a lot of conjugation that lowers the HOMO LUMO gap. It takes less and less energy till finally you're in the visible range, like 533. So all our neat dyes here absorb in the visible range. Indigo, you want blue jeans, but notice this absorbs in the red. Dye absorbs this, so what color does the item appear? Appears blue. UV visible analysis in biology and medicine. UV visible spectroscopy is non-destructive, exceptionally sensitive, and we use it to measure concentrations, not to figure out the purines in our sample, but if we have biological samples and we know these things are there, we can use it to quantify various things. Purine, where do you find purine? Yeah, it's one of those bases.